Hello, I'm Dr. Fergus Donahoe, and in this video we're going to be looking at how to prove the rule of distribution using conditional proof. The rule of distribution is one of our rules of replacement, and you can see both versions right here. This one says that P and Q or R is materially equivalent to P and Q or P and R, and the second one says that P or Q and R is materially equivalent to P or Q and P or R. You are currently watching For the Love of Wisdom, my YouTube channel on free thought, philosophy, and critical thinking. Besides videos on logic, you will find videos on science, on ethics, on religion, and on happiness on this channel. This video is part of a series of videos on symbolic logic. The first video began with a general discussion of what makes an argument a good one. And one of the qualities that made a deductive argument a good one was being valid. A valid argument is one whose premises entail its conclusion. In the subsequent videos, we looked at rules of inference, which were forms of arguments where the premises entail the conclusion. And then we moved on to rules of replacement. Rules of replacement tell us that we can replace one expression with another expression that has the same truth value. And we can do this within a line as well as from one line to another. And then we moved on to doing proofs with the rules of inference. We cannot collect enough rules for all the arguments we might come up against. So we start with a simple set of rules, and then we start to do proofs using those rules to handle other arguments that we may come up against. And after we learned how to do proofs a bit, we moved on to learning how to do conditional proof. And a conditional proof is a method for proving a conditional. A conditional is an if-then statement, and we assume the if part of that conditional and try to derive the then part. And if we can do that, then we can show that the conditional is actually true. And over here, our rules of replacement are represented by biconditionals. A biconditional, as you can see here, is equivalent to the conjunction of two conditionals. And we could prove each of our rules of replacement by using conditional proof to prove each of the conditionals as equivalent to, and then going from there to the biconditional. And so we started proving rules of replacement with this video. With this one, we just did the rule of tautology, which is a very simple rule. And then I gave you some homework, which included doing some proofs of some other rules of replacement. And here in this video where we go over the solutions, these are the rule of transposition and the conjunctive forms of commutation and association. In the next video, the rules of inference for biconditionals, we introduced some rules for introducing and eliminating biconditionals, and we use these in proofs for the rule of material equivalence. And you can see both versions of that rule right here. In the next video, we did a proof of the rule of exportation, which involved the nesting of conditional proofs. And in proving disjunctions with conditional proof, we went over proofs for the disjunctive forms of commutation and association. And that leaves us with 4 rules of replacement left to prove. And in this video, we are looking at the rule known as distribution. So let's take a look at that. And I have to adjust this. So here's one version of the rule of distribution. We have P and Q or R is materially equivalent to P and Q or P and R. And we're going to start by assuming what we have on the left side of the biconditional, and we'll try to demonstrate what we have on the right-hand side. and then we'll go in the reverse direction. So we start by assuming P and Q or R. And what we want to prove now is P and Q or P and R, this expression right here. And this is a disjunction, and we just learned in the previous video how we could use conditional proof to prove a disjunction. So let's try that. We begin by assuming the negation of the first disjunct in our disjunction, and that is the negation of P and Q. And now we want to get P and R. Well, P is readily available in the first premise. So we can just get that through simplification. And now we want to get R. Well, R is contained in the second conjunct of the first premise. So let's simplify it again to get that. And we get Q or R. Now R is a disjunct here in line 4. And we can get a disjunct from a disjunction using disjunctive syllogism. And to do that, we're going to need not Q. So how can we get not Q? Well, look up here at line 2. This is equivalent to not P or not Q through De Morgan's. So that gives us a line that has not Q on it. And then we could use disjunctive syllogism to get not Q from this line. To do that, we're going to need the negation of not P, which is not P. And we can get that by double negating line 3. And now that we have not P, we can get not Q through disjunctive syllogism. And with not Q in hand, we can get R through disjunctive syllogism. And now that we have both P and R, we can conjoin them together to get P and R. And that was what we were looking for. So we can close off this conditional proof, and we get if not P and Q, then P and R. And we use material implication to change this into a disjunction. So we get not P and Q or P and R. And then we use double negation to turn this into the disjunction that we were looking for. Now there is actually a quicker way to do this part of the proof. It involves only 10 steps instead of 12. And so I'm going to skip over to where I've done it that way and continue the proof that way. Okay. I'm starting the proof over here because there is a shorter way to do what we just did. So again, we begin by assuming P and Q or R. And we want to get the disjunction over here, P and Q or P and R. And what we just did was use a conditional proof to prove the disjunction. Another way to get a disjunction is using a constructive dilemma. And to get a disjunction through a constructive dilemma, we need another disjunction and we need two conditionals. Well, we have a disjunction right here, Q or R. And we're also going to need P here. So let's simplify this 2 times. We simplify it once to get P, we simplify it again to get Q or R. Now, we want to get the two conditionals. We want to get if Q, then P and Q, and we want to get if R, then P and R. And once we have those, we can use a constructive dilemma to get this disjunction. So let's begin by assuming Q. And now we just use conjunction and we get P and Q on line 5. And we can close off this conditional proof when we get if Q, then P and Q by conditional proof. And that is one of the two conditionals that we need to use a constructive dilemma to get this conclusion. And now we assume R, and we use conjunction to get P and R. And then we use conditional proof to get if R, then P and R. Okay, and now we have the two conditionals that we need for a constructive dilemma, and we have the disjunction we need for it. So we're all set. and we use constructive dilemma to get P and Q or P and R. And then we can use conditional proof on lines 1 through 10, and we get if P and Q are R, then P and Q or P and R. And that saved us 2 lines here. Now we'll continue from this proof and go in the other direction. So we begin by assuming P and Q or P and R. That's what's on the right side of the biconditional. And we want to get P and Q or R. So how can we get that? Well, what we want to prove is a conjunction, and we can prove a conjunction by proving each of the conjuncts of that conjunction. Now let's start with Q or R. Q or R is a disjunction. We know we can prove a disjunction using a constructive dilemma. And we have another disjunction over here. So if we can get if P and Q, then Q, and if we can get if P and R, then R, then we can get Q or R by constructive dilemma. So let's go ahead and do that. So first we assume P and Q, and then we get Q through simplification, and we can close off that conditional proof and get if P and Q, then Q. And now we assume P and R, and we get R through simplification. We close off that conditional proof and we get if P and R, then R. And now we can use a constructive dilemma to get Q or R. And that's from lines 12, 15, and 18. So up on 12 we have our disjunction, and on 15 and 18 we have 2 conditionals. Now how are we going to get P? Well, it turns out that P is equivalent to the disjunction P or P. And we can use the same method to get P or P that we just used to get Q or R. So we'll go ahead and do that. And once we get P or P, we can just change it to P. So we assume P and Q. And then we simplify that to get P. And then we get if P and Q, then P. And then we assume P and R. We simplify that to get P. And we close off this conditional proof when we get if P and R, then P. And now we have 2 conditionals here. And we have the disjunction up on line 12. And we use those to get P or P through constructive dilemma. And then we use the rule of tautology to change that into P. And now that we have P on one line and we have Q or R on another, we can use the rule of conjunction to get P and Q or R. And that lets us finish this conditional proof, and we get if P and Q or P and R, then P and Q or R. And finally, from lines 11, and I'll go back up so you can see it, line 11 up here, and line 29, we can use biconditional introduction to get the biconditional that we were looking for, which is one of the versions of the rule of distribution. P and Q or R is materially equivalent to P and Q or P and R. And now we'll go ahead with a proof of the other form of distribution. This one says P or Q and R is equivalent to P or Q and P or R. And we'll begin by assuming what we have on the left side of the biconditional and try to get what we have on the right-hand side. So our assumption is P or Q and R. And looking at what we want to get, we see that it's a conjunction. And it's a conjunction of 2 disjunctions. We can get each of these disjunctions by proving the conditional that each one is equivalent to. So we're going to use a conditional proof to get at each of these disjunctions, and once we have them, we'll use a conjunction to bring them together. So we start by assuming not P, because we want to get if not P, then Q, which will be equivalent to P or Q. So now that we have not P, we want to get Q. And Q is up here in this disjunct of this disjunction, P or Q or R. P or Q and R. And we have not P, which is the denial of the first disjunct here, so we can use disjunctive syllogism to get Q and R. And now that we have that, we can just simplify it to get Q. And that lets us close off this conditional proof, and we get if not P, then Q. Through material implication, we change that to not P or Q. And through double negation, we change that to P or Q, which is the first disjunction that we're going after. And now we assume not P once again. And once again, we get Q and R through a disjunctive syllogism. And that is incorrect here. It's not lines 8 and 9. Okay, I've just corrected the line numbers here. The disjunctive syllogism is from lines 1 and 8. And we get Q and R. And then we simplify that to get R. And then we close off this conditional proof and we get if not P, then R. And we change that to a disjunction through material implication. And we get rid of the two negation signs with double negation. And now we have both P or Q and P or R, and we can just conjoin them together on line 14 using conjunction. And that lets us close off this conditional proof, and we get P or Q and R, then P or Q and P or R from lines 1 through 14. Okay, let's move on. Now we assume what we have on the right-hand side of the biconditional, and we're going to try to prove what we have on the left-hand side. And looking at what we do have on the left-hand side, we see that it's a disjunction. And we know how to prove a disjunction by proving the equivalent conditional. So let's go ahead and do that. We're going to begin by assuming not P. And let's see. And we want to get Q and R. Okay. So how can we get Q and R? Well, if we take a look at what we already have, we see that we have a conjunction of two disjunctions. And in each of those disjunctions we have P, but we also have an assumption of not P. Maybe I just got ahead of myself. We're assuming not P here because we want to be able to get Q from this disjunction, and we want to be able to get R from this disjunction. And no, I'm not getting ahead of myself. I'm getting behind and ahead of myself and getting mixed up. I already assumed not P because I'm trying to prove a conditional that has not P as its antecedent. But not P is going to come in handy here for getting Q and R out of line 16. Okay, so we move on to line 18, and we get P or Q by simplification. And now we can get Q through a disjunctive syllogism. And we're going to do the same thing to get R. We get P or R through simplification. And we get R through a disjunctive syllogism. And now that we have Q and we have R, we can conjoin them on line 22 to get Q and R. And that's what we're going for. So now we can close off this conditional proof and we get if not P, then Q and R. And we now want to change this into a disjunction. And we get rid of the two negation signs by double negating it. And now we can close off this conditional proof. And we get if P or Q and P or R, then P or Q and R by conditional proof. And finally, we have the two conditionals we need. We have one up here on line 15 and one here on line 26. And we use biconditional introduction to get the biconditional P or Q and R is equivalent to P or Q and P or R. And that ends this proof of the rule of distribution. And now let's take a look at the rules that we have not yet done proofs for. And I will fix this here. Okay, so these are the remaining rules that we haven't done any proofs for. We have double negation, we have material implication, and we have De Morgan's. And you may notice that one of the things these three rules have in common is that each has a negation sign in it. And not only that, but, well, yeah, each has a negation sign in it. Sometimes it goes from a side having a negation to one not having it, like here or here. And here, while there's negation signs on both sides, what the negation sign negates changes from side to side. And we're going to be introducing a new rule we can use called indirect proof. This is a method for proving the negation of something. So if we want to prove something, we assume the opposite. We try to derive a contradiction, and then we conclude what we were trying to prove. Because if the contradiction of something leads to an actual contradiction, we know that that can't be true. So what we're trying to prove must be true. You know, if our assumption leads to a contradiction, our assumption cannot be true, so its opposite must be true. That's how that works. So getting back to these three rules, one of these rules can be proven using the equipment we currently have, which is the rules of replacement, the rules of inference, and conditional proof. And the other two, as far as I can tell, cannot be proven unless we bring in the rule of indirect proof. So take a look at these three rules of replacement. Try to figure out which one you can actually prove given the equipment we have right now. And if you can figure that out, you'll begin to get an idea how we can use indirect proof. And try to prove the others if you can, and come back for the next video or the next lesson and learn how these are done. Let me remind you, down below is a link to the blog post for this video, which goes over the same material. So check that out if you like, and check out the other videos in this series if you haven't seen them yet, and if you somehow decide to watch this video without watching them. And thanks for watching, and we'll see each other next time, or not, because sight doesn't work this way. Okay, but you know what I mean.